All right, here's a video on Bernoulli's equation, and we're going to apply it to a pitot tube, okay, or a pitot probe. And these are really mounted on airplanes, and they're used to find the velocity of the plane, okay. So I'm going to zoom in right here. So the way the pitot probe is it's like a 90-degree elbow. Think of it as a 90-degree elbow. And there are two places to measure pressure. Right here at this entrance and right here. And this is a tube, and there are probably 10 holes or so at that location. Okay, and it's actually downstream from this. It's not right at the front. It's down a certain distance. About 10 holes, small holes all the way around. And this is where we measure the other pressure. Okay, so they're hooked up. Like this is a separate pressure. Hooked up to this pressure sensor. And then this other one is hooked up here. And that's kind of around that other tube. And they're hooked to the other side. And you actually measure a delta P. All right, so let's analyze and use Bernoulli's on this pitot tube. And what we're going to do is we're going to put a state way upstream. We're going to label it 1. And we're going to label state 2 right at the entrance of this center tube. Okay. So pitot tubes. Well, let's sometimes it's easier to kind of show you. Here's a wind tunnel. And wind tunnels are basically a place where you can create a small scale airplane, mount it on what they call the sting, turn a fan on, and have the air blow over this plane to look at lift, drag, and all that stuff. Okay. Now, inside this wind tunnel, typically they put a pitot tube. Pitot tube. It looks like this. It's a 90-degree tube inside a tube. And they put it in here. Now, I don't know if they have one in this one. This is a different photo, but they probably do. But they keep that in there, and they use that to calculate the speed of the air going over the jet, or the scale model. So, if you notice, whoops, that's why in this pitot probe, I picked point 1 way upstream and point 2 right at the center of that center hole, okay, because it's a hole. All right, like if I zoomed right in here, there is that hole right there, and that runs to a separate tube to a pressure gauge. And then back here, there are little holes all the way around, and that runs to the other side so you can measure delta P. Okay, it's pretty cool. Pitot probes are pretty cool. So we can write Bernoulli's P1 over rho plus V1 squared over 2 plus GZ1 equals P2 over rho plus V2 squared over 2 plus GZ2. What we can do is we can cancel some things. All right. Elevation changes are gone, so we don't have to worry about that. The term on the left, we will have what we call a static pressure. Okay, that is your like standard room pressure. Okay, we can probably use the ideal gas equation to find the pressure. And this is what we call the dynamic pressure. Okay, typically, I'll show you here in a second. I've kind of written it quite a little bit wrong, but that's fine. And then on state 2, what we do is there is actually what we call a stagnation point. There's no velocity here. It comes to a rest. So from point 1 to 2, it slows right down and stops. Okay. And so there's no velocity right here at that entrance, which I'm calling point 2. Okay. All right, there is no velocity. It's what we call stagnation. So we only have this, and this is kind of what we call total pressure. Okay, Typically, what I should have done is multiplied every term by rho. So P1 plus rho V1 squared over 2 equals P2. So this is your static. This is your dynamic. And this is what you call total pressure. Okay. So we can rearrange this equation, which we can get 2 delta P over the density. So we use Bernoulli's. We have now an equation for the velocity of the air going over that scaled model. Okay. And a couple things. Pretty much what happens is this is called a streamline. It's the way a particle would move. It'd go like this and go a little bit around and then level right out. Okay. So technically this point right here that we're measuring is the same as point 1. Okay. Because it's perpendicular to the surface and there's a velocity to this. Okay. It's moving past it and we have static. So we have this condition right there at point 1. Point 2, it just comes and stops. This is no velocity, and we have total pressure. Okay. And if you mount this pitot tube on an airplane, okay, we know that we can use point 1 here and point 2 here. We can model it, and you get the same equation. Okay. So it doesn't matter if you're in a wind tunnel or if it's mounted to something. Because we know that point 1s are kind of both at those states, you can manipulate and find this equation. So I'm okay if you know, okay, it's a pitot tube, just go ahead and use this equation right here, square root of 2 delta P over rho. Okay. So I hope this helps with the pitot-static probe. They are very useful. They're used on planes, and you could mount one to your car and calculate the speed of your car if you wanted to. All right, if you have questions, let me know, but you now have the pitot tube equation that you can use in your homework.